except for the prices that they have. And we have one fraction of firms' data that does not change or has not changed their prices in this period, and one fraction that the remaining fraction, one minus data, changes their prices, updates their price. So inflation is driven by a large portion of firms changing the price, and those who can't change the price choosing a large price increase. So now we need to figure out what that price increase is going to be. See, I can tell it's not Coca-Cola. I wasn't kidding with that. So let's first consider the case where we don't have the price regime. So what would firms do who want to optimize, they were trying to maximize their prices? Now they're going to maximize profit. Their profit is given by revenue, price times the quantity they sell, minus their cost. What is our cost function? So let's look at an individual firm I. So new rigidity firm I that wants to choose PTI to maximize the revenue of selling its good. Right? It sells good I at price PTI minus here our cost function y or psi of YTI. Now we can get to the our firm knows that it faces this demand function. So it's going to sell YTI, as many of its goods as are demanded, CTI. We're not going to have government or investment or export. So right now, government, investment, or exports. We'll add an exports towards tomorrow and think a little bit about investment the day after that. Alright, so YT equals CT, and it holds for each good individually as well. It's going to take the demand function into account. And it knows if it raises its price, people are going to demand less of its good. Apple isn't surprised that people are buying other goods too because their prices are more expensive than other goods. It's very well aware of that. So let's see how we get to the optimum here. So let's substitute that in. Here also, this is YTI. Let's get rid of this YTI by substituting in the demand function. and we get PTI 1 minus epsilon PT epsilon CT minus bracket here, PT I over T minus epsilon CT. And we're just choosing PTI. All right, so let's take the derivative with respect to choice variable, set that equal to 0, and we get, well, it's simple, pull this down, 1 minus epsilon, subtract 1 from the exponent, here we have the inner derivative, times the outer derivative times then the inner derivative, which is then epsilon, we have et I minus epsilon minus 1 over et minus epsilon times ct. We should recognize, well, this is simply YTI. And this is YTI divided by PTI. All right, so we can divide through by YTI, multiply through with PTI, and we get 1 minus epsilon PTI plus epsilon marginal cost, or PTI equals epsilon over epsilon minus 1 times marginal costs. In this setup, prices are a markup over marginal costs. And so we can do the thought experiment. What does the new iPhone going to cost? Let's figure out what Apple thinks about our epsilon. Did you know that the iPhone 17, does anyone know what the price is supposed to be? Like, you can look real fast, like, what's the number? 50 million?
50.
Right, something like that.
Yeah, 50.
25 million, huh? You sure for the new one? Yeah, okay, so we have 25, or let's call it epsilon. Epsilon that's supposed to be now. It's just epsilon over epsilon minus 1. What do you think it costs Apple to produce one of these iPhones? Marginal cost. What is the cost of producing an iPhone? I think the labor cost, where he has to get the transistors, the parts, he has to put everything together. Maybe. I'm sorry? it's the much higher. It probably cost them something like 50 euros. That's maybe 1.5 million. Right? Let's just say, let's make it 1 million to make the math easy. Right? You can go there. So this means that we have a markup of, it's 25 times, right? The marginal cost. Right, if we solve it for epsilon here, right, then we get epsilon minus 1 and 25 equals epsilon, or right, 24, epsilon equals 25, so epsilon equals 1 and 1/25. So it's a little bit larger than 1. And even if this number was a lot less, let's say the iPhone costs 2.5 million to produce. So the markup is only 10 times, then epsilon would still be, what is this? This is 1.04. Right? Then this would go up to 1.1. Yeah? Right? So it's not going to make, it's very, very, very close to 1. Right? This elasticity. This elasticity is defined from 1 to infinity. So we're already pushing, it's very inelastic to substitute, which is why maintaining this inelastic substitutability is very important for Apple. They don't want competition on their iCloud services, or they have their own. They don't go on the App Store. They have the Apple Store. It's very important for them to protect this space, to keep this elasticity very, very low. I worked at a pizza restaurant for a long time, and there we had to charge $8 for a pizza, and our costs for pizza were about $5. We were generating $3 of profit for each pizza that we sold. Right? 8 plus 1, 8 equals epsilon times 5. Right, so we get that epsilon equals 5/3. Right, we're getting closer to 2, but it's still a number between 1 and 2. Right? So for a lot of these companies, right, and they have to make our pizza. It wasn't any pizza, it was a special pizza, it was a particular brand. Miranda Pizza is now owned by this company, or they're owned by the same company, or it used to be, or something like that. Yeah? All right, so if you think of this parameter epsilon as being defined from 1 to infinity, we have a lot of companies that are bunched up trying to get as close to 1 as they can, because that's how they're going to make large profits. But so now, okay. So how about then in our setup? So this would be the case if we don't have any rigidities to prevent us from changing our price. But we do. We have sticky prices. So what does our firm, what do the sticky prices do? Well, it's going to maximize profits, right? Just like in the standard case. Right? It's profits, you see recognize the profit function in here, but now it's going to take into account when it changes its price in period t, it might be stuck with this price for a while. Okay? So if I'm given the opportunity to change my price today, I'm not just going to set the optimal price for today, based on today's profits. I'm going to take into account that this price might be around next period, or the period thereafter. Imagine a world where you knew that there was going to be very high inflation. Right? Maybe not Germany, Zimbabwe, hyperinflation, but imagine that you knew the prices were going to double over the next year. If you chose the price today that would be good in the world where prices are double, to be twice what would be optimal today, that would be too high for today. You'd lose a lot of customers. If you choose the optimal price, it would be optimal based on today's price level. It would be optimal today, but if you're stuck with that price tomorrow, if you don't change your price tomorrow, then it'll be way too low tomorrow. All the other prices have doubled, and you'll sell your price, your good at a way too low of a price. So you're going to try to find a price that takes both into account, that's going to weigh them. Yeah? Right, so we're going to take the price level, or the profit function today, next period, the period thereafter, and the period thereafter into account. Let's just draw just that statement that I just made. Let's look at that. T plus 1. So let's say optimally what we would choose would be a low price today and a high price tomorrow. So this would be our optimal flexible price. Right, so we know that the price level is rising tomorrow, there's inflation, so we can set the price today, but tomorrow comes around, we want to raise our price. But now we're being asked to choose the price that we would have to keep in both periods. Right, if we choose this price, right, too high in T. If we choose this price, it'll be too low in T plus 1. So if this price is too low, or too high, and this price is too low, the best price is going to be somewhere in the middle, right? Right, we're going to choose some price like that. Okay, and now we want to think then, bit by bit, what's going to make this black dotted line, so now I'll call this our optimal fixed price. What might push that optimal fixed price higher, or this optimal fixed price lower? How about the probability of being chosen to change your price? If the probability that you're going to be selected at random to be a firm that gets to change its price, if that probability is very, very high, then the probability that whatever price you choose today will still be around in T plus 1 is pretty low. So it's very likely that when T plus 1 comes around, I'll get to change my price again anyway. In that case, as I'll be setting the price closer to the price here. Indeed, if theta goes to 0, then there's a 100% probability I'll be able to change my price tomorrow. So, chosen at T. Then I will set the price today equal to the optimal flexible price today. Right? And if as theta gets larger, and I'm more likely to be stuck with the price tomorrow, and it's going to go higher. Or maybe there's something else that would push this closer to the time t flexible optimal price. What if I just don't care about tomorrow? Well, when might that happen? We've thought about this from the household perspective, right? This is the discount factor, right? Our impatience. Well, who owns the firms, right? You and I do. It's us, right? In some sense, in the end, and however if we divide this world up, we have as people. Every firm is owned directly or indirectly by some people, right? So this firm, when it starts to think about time, it's going to be, or we're going to assume it's going to think about time in accordance with its owner's preferences. All right, let's look back at the maximization problem here. We have this first term here. We have profits today and in future periods. These future profits are multiplied with theta to the power of k. Theta is the probability that our price will be fixed. The price we choose today will be stuck with it k periods from now. So as theta goes down, price rigidities go down, we're less likely to be stuck with our price in the future. Right? So we're going to pay less attention to this future optimal situation, and we'll just think about today's profits. Right? If theta goes to 0, then only the first term remains. Now we have theta to the power of 0 is equal to 1. The second term is the stochastic discount factor. We thought about this when we were pricing assets. Right? This is the stochastic discount factor between period t and period t plus k. It's the measure of our household's discount factor and marginal utility from a nominal asset. Essentially, our household has the option to own the firm, which means that if the firm makes a profit, the household gets a share of this profit. Right? So it's ownership of the stream of profits. Right? Or the household could buy a bond, right, as alternatives. So when it's comparing these two different assets, we're going to have a sort of arbitrage. But remember, when our household isn't risk neutral, our household cares whether it gets a free meal when it's hungry, or whether it gets the free meal when it's not hungry. That makes a difference to the household. So we have in our stochastic discount factor, beta, and then the ratios of marginal utilities from consumption. Yeah? The same thing we did in the asset price selection. Okay, and now if you look more closely, wait a second, this isn't just different profit functions, it's the notation here. We're choosing a price today, PT star, the price today that we are hypothetically going to be stuck with out k periods. And we're then multiplying it with the revenue that we would expect in k periods, conditional on us having last chosen our price in this period t. Because of course our demand, the demand that we face in period t plus k, is going to depend on how this price that we're choosing today for the future, that will remain in effect in the future as well with some positive probability, how it relates to the price level, which is going to be changing over time. And then likewise our cost as well. Right, so we are maximizing, in essence, from our households, we were maximizing the sum of expected discounted lifetime utility. Our firms are now maximizing the sum of expected discounted lifetime profits, right, of the price that they're choosing now.
Professor, can you go back to the previous slide? And questions.
Yeah.
So we only need to care about in the next period, we can, there are 1 minus theta chance that we can set the price again, because we don't care about that, because it needs to be some kind of constant, right? Because we will,
We then re-optimize.
yeah,
Right, so this is the problem we choose. So that's a very good question. So where's this 1 minus theta stuff? Why do I only see the theta here? We're just looking at first one portion of the decision, and we'll figure out what the rest follows from. So with probability 1 minus theta, we're solving this problem. With probability 1 minus theta, we've chosen today to choose our price. We're going to choose our price today, PT star. All right, when we choose our price today, PT star, we want to maximize today's profit, which will show up here with k equals 0, this is 1, and this is also 1, so we're just going to have our today's profit. But there's also a probability, theta, that we'll be stuck with this price again tomorrow. And so we want to choose the price today, but like that is going to be good for the case that we're stuck with this price 1 period, 2 periods, k periods. So now let's look at tomorrow. Tomorrow comes about either we're stuck with the price we chose last period, okay, in which case tomorrow, so in t plus 1, firm I is going to have PT star. Right? Okay. With probability 1 minus theta, tomorrow, this firm gets to choose its optimal price again. So it's going to solve this problem, but 1 period in the future. Right? So this sums up everything, and this 1 minus theta is what allows us to do this in essence. And to have the choice to solve this optimization problem. So if at any period k, we are part of the 1 minus k, we throw out this PT star, and we solve for PT plus k star. We re-optimize, we now choose the price in this new period. Does that make sense?
yeah. And we treat the theta here as exogenous?
Yeah, the theta here is chosen as exogenous. The probability of being selected is exogenous. And this is, so there's a whole big literature on different ways to do price regimes. And this is one of the biggest criticisms, right? Or one of many big criticisms. I don't know if it's the biggest, but the probability of not adjusting the price is an independent event. You're chosen at random. It's a lottery with the firms are chosen who can change the price, who cannot. It's like a magical fairy comes and taps you on the shoulder and says you can change your price. Some people call it the Calvo fairy, to make fun of it. Why is this maybe problematic? Well, when would I choose to adjust my price? Well, maybe if inflation, the higher is inflation, maybe the lower this probability should be. Right? Indeed, if you go to countries with higher inflation, you tend to see more frequent price adjustments. This kind of makes sense, right? If the price is changing a lot, the price level, we're going to want to update our prices more frequently. Maybe that would be one example of what's called state-dependent pricing. Maybe we would look at our own optimization problem. As our profits start to go down, right, we would then be more likely to change our price. So if we notice, we'll notice when our price is wrong because we're not making a profit anymore, right? Or our profits go down very quickly, right? So maybe this theta should depend on last period's profits or this period's profits relative to some benchmark, right? It's expensive to change our menus or to run the study to figure out what the optimal price for our VIN phone should be, right? But we'll notice perhaps when we need to make an adjustment. Not here. Theta is assumed exogenous parameter. It's you either get chosen or you don't. It has nothing to do with anything else. Well, that's kind of disappointing, isn't it? Yes and no. Jordi Galli, I saw his presentation, said, look, think of this. This is really just the first approximation as to all of the different reasons, the stories that I was telling you for why firms might not adjust their prices. we can extend this in all sorts of other ways. It's always the question, what do we get for the price that we pay? So imagine, right, your Google Maps is wrong, but it moves very, very quickly. What if, it misses all the leaves on all the trees, right? Imagine if to use Google Maps to go from one place to another, it first had to render graphically the leaf on every tree on the route between where you are and where you want to go. Your cell phone would be calculating for a couple of days until it rendered all the leaves on the trees, and then it could calculate your path from A to B. Maybe that's not so important, right? Having that level of accuracy. Right, so the idea here, right? This is as we'll see. This is going to give us a very straightforward, quick way of getting to the core of the transmission mechanism. But you're absolutely right. It's an important thing to think about. Okay, our stochastic discount factor, we can think of this, right, we can arbitrage. Alternatively, we could invest in a nominal security for k periods, right, which is going to give us, based on the marginal rate of substitution between period t and period t plus k, with our utility function, right, with our constant relative risk aversion parameter of sigma, is equation 20. And the assumption being here that the firms are owned by the household. So the household is going to discount or price future profits using this equation. And again, so imagine you're in a firm and it pays out. It makes a profit, so you get a dividend exactly when you're hungry. That's very valuable. Or exactly when you lose your job. And so think of a firm that generates high profits during recessions and low profits during boom times. Right? This might be a valuable stock to own compared to another firm that makes on average the same profits, but makes large profits in a boom and losses during a recession. Because exactly during the recession is when it's harder to make profits, when you might lose your job. Right? So it would give you some sort of insurance premiation, right? And that's exactly what's built into this stochastic discount factor here, 20, which means that a firm, when it's comparing, well, today's profits versus tomorrow's profits, it's going to discount them in a couple ways. One, well, what is the probability that I'm even going to be stuck with this price tomorrow? That I should even be worrying about it, right? With probability 1 minus theta, I'll get chosen anew next period to change my price. Then all this won't matter. Okay. Then, well, let's say I do get stuck with this price. I'm still stuck with this price tomorrow. How important is tomorrow's profits versus today's profits? Well, it depends on our households, my owners' impatience, which we have with beta, and it also depends on how they're going to value profits tomorrow versus today. There might be an expectation, reason to think that tomorrow is a recession, when our household might have a high marginal utility from consumption. It might really value, if our household, my owners really, really would like a profit tomorrow, relative to today, because tomorrow a recession is coming, maybe I should choose this price to be closer to the profit maximizing price tomorrow. Because my household, my owner, is going to highly value consumption tomorrow in expectation. So all this is built in, and it's no different than any of the other asset pricing that we were doing last week. Okay, so we can substitute in the demand function like we did for the flexible price case. Right, so we have our price times this is the revenue. Revenue with our demand function in 22. And now we take the first order condition, and we get equation 23.
Well, I think the y, we have like t plus k conditional, until but not the c, t plus k.
This is the aggregate. Remember, the assumption is for this firm. And so this would be This is the demand in period t plus k for the goods of a firm that changed its price in t. Remember, the goods only depend, the difference between the firms is only what their prices are. So it's the demand for this firm's price, or the demand for this firm's good depends on when it last changed its price, which was k periods ago. And this is aggregate demand. This is the demand for our consumption basket as a whole. Right? So this is going to be given in general equilibrium. So we're trying to figure out, are there the consumers demand more of goods whose price was last changed k periods ago than average this period, or less? And that's going to depend on how their price is relative to the aggregate price level of the basket. Price of the basket. And again, this is why choosing these infinitesimally small firms was so important, is that we can treat these aggregate variables as exogenous to the optimization problem of individuals. Right? They have no influence, they have to take this as given. And when we take our first order condition, we get to an equation that looks a lot like equation 23. So double check, I think I'm going to do this together anyway. We're going to work on that together. Anyway, so see if you have a little bit of time. See in particular if you can get from 22 to 23 using what we've done here. Okay? But what you see in equation 23 is the price that we end up choosing is a price that's trying. Right? If you look at this, if we didn't have any of this sum business here, if we just had period t here, the optimal price, which this is 0, would be equal to this markup over marginal cost, just like we saw here. Right? So this part here is the what I called optimal flexible price. And it's going to change in each period, t plus k. And we're trying to find this pt star, right? This dotted line that's going to stay constant across time, right? To match, right? To set this equal to 0. Right? So we're weighting the objective of the optimal price in today's world versus what we think is going to be the optimal price tomorrow's world, and the optimal price of the day after tomorrow's world, the day after, and the day after, and the day after that. And we can already do a little bit of policy analysis. So let's start off in a world with different periods of time, and where the path of this optimal flexible price is constant at its level now. And monetary policy, for example, makes an announcement that starting next year, we're going to double the rate of money supply creation. So this would mean in a world with flexible prices, so this is next quarter, half a year from now, figures it next This is now the path of these optimal flexible prices that we see. Now, in the world we started off with, all future optimal prices are constant. Then the price that we choose today, when we're given the chance to change our price, is also constant, right? The ship's, the nice heading, even seas, we're not going to change anything. Everything's fantastic. And now, we get warning that there's danger ahead. If we have, in a world where we have perfectly flexible prices, what happens today? Nothing. The central bank says in a year it'll start increasing the money supply, so then in a year I'll start increasing my price. And every firm thinks this way. Right? And that's what every firm will do. We're in an optimal, flexible world. What happens in our world? You're a firm today, you've heard the announcement, wait a second, yeah, I'm going to change my price. Why? Because there's a non-zero probability that when this starts happening, I won't be able to change my price anymore. So maybe, right, the optimal price is, when I solve that problem there, is this. This picture right here is the intuition behind the entire new Keynesian model. What has happened here? A policy announcement of something in the future has an effect immediately. The effect doesn't only happen once the change in policy actually takes place. The mere announcement of this future policy action going to happen takes an effect now. Our price setters, because they are afraid of not being able to change their prices in the future, take everything that they think is going to happen in the future and front load it today. They pull it forward, they front load. Right? We're making a decision today, and we're forward looking as a firm. We take into account the central bank has said something's going to start to happen, and we can think, well, wait a second, what if the central bank ends up not following through on this? Well, this tells us again expectations management, right? That's okay, they might lose credibility. At this point in time, we calculate our price not on the knowledge of certainty that it will go up, but there's some possibility that they might follow through, that it might happen. So there's an expected increase, maybe not one for one, because we take into account that it might not happen with certainty. But if anything, right, we know that our forward-looking price setters will raise their prices today, immediately. Right, there's some good examples. I haven't looked at the data, but this is also why, right, I said COVID was horrible for us as people and humanity. Terrible, terrible time. But for the economics profession, it also had a positive side effect, and then it gave us lots of data. Right? There's this exogenous change, right? And countries responded differently. Right? So there's different treatment and different responses. So we learned a lot and continue to learn that. We're still in the financial crisis. Now imagine if the leader of some country on one day says, starting in 6 months, we're going to increase the tariffs on a whole bunch of different countries at different rates. Right? Sometime in the future, we're going to be raising the prices that some consumers see in these goods. Yeah? This theory makes a prediction that we could test. We could look in the data. Did prices for some goods, particularly in the United States, for imported goods, did they react immediately? Did they start to go up immediately? Or not? I'm not sure. This theory would tell me that I'm in the United States and I'm a company that uses lots of parts or that sells goods from many different countries. When that announcement was made, I probably would started raising my prices immediately. I wouldn't wait until the tariff actually was implemented. I would have raised it immediately, unless you think there's no credibility in what this man was saying and promising. Yeah, right. But we have some testable implications, right, of this theory that we can now apply right to the data. So it's really something I'll look at tomorrow. Right, and we get this baseline markup, the flexible price markup. We call it in the book, this is called the frictionless gross markup, M. And the reason why is that our firms are going to end up having different markups over time. Right? If I choose a price and the price level is higher than expected, but I can't adjust my price, this means that my price is too low relative to what it should be. I.e., my markup is not going to be this markup, but it's going to end up being a lower markup. So another way, and the way some authors really like to look at this model, is firms trying to realign their markups to this frictionless markup. They want to make sure that the prices are keeping up with their costs. All right, again, we get back to the neoclassical model in the limit as epsilon goes to infinity. Right, epsilon very large over epsilon minus 1 very large. Right, if this is 1,000 divided by 999, that's almost 1. 1,000,000 over 999,999, even closer to 1. So you can see where this is going as epsilon goes to infinity. We have a gross markup of 1, which means that our prices are equal to marginal costs, which is micro 101, yeah, for perfect computation. All right, so now we want to. This is it's a complicated object here. Right, the individual components, I think we can understand rather straightforwardly, but to resolve this, we have expectations, sums of lots of terms that are going to be correlated with each other. Right, and the product of these, this is not something we're going to be able to resolve easily. So we're going to log linearize this like we're log linearizing all of our other variables. So let's log linearize around a steady state where we have zero inflation. So let's be in a world where on average we have perfect price stability. So no inflation, prices stay the same, and we're going to look at a small deviation from this equilibrium. This zero inflation steady state is very useful because it's going to eliminate a lot of constants that we would otherwise have to be carrying around with us. What this also means is that in a steady state, the optimal price. Right, so the optimal price adjustment is 1. Right, prices don't change either on the aggregate or in the individual. All firms then are going to have the same price. All firms, this price is equal to the average price or price level. All firms are going to face the same demand. And all firms are going to produce the same output. Which means if we look at real marginal costs, divide this through by PT, we get real marginal costs and like a relative price. But in in zero inflation steady state, I equals P. All right, so we get that 1 is equal to a markup times marginal cost. real marginal costs. And also we saw this in Lagrange in the Euler equation, right? The Euler equation that we have for Household's problem is just the acid pricing equation for pricing the value of this nominal discount bond. Where this stochastic discount factor comes in here to the valuation of profits at any given future point in time. The household is just another asset. And we also saw there that we get beta. Is the only part that remains in steady state. There we were comparing an investment for 1 quarter. Here if we compare QT to QT plus K. Right, so the value today of profits K periods in the future is simply going to be discounted by our discount factor to the power of K. All right. We can write this in a Taylor approximation as equation 26. And we have the optimal log price adjustment is equal to a weighted average of all current and future nominal marginal cost. Yeah, nominal marginal cost. This is the real marginal cost deviation from its steady state. Right, and this gives us change in prices of these periods. A weighted average. What's a weighted average? Well, what's an unweighted average? An unweighted average. Sorry, let's call this x bar equal to x1 plus x2 divided by 2, right? Or maybe it's 3, x1 plus x2 plus x3 divided by 3. What are we doing? We are multiplying each term with a weight that is the same for each term. And you notice how these weights, if I change the number of objects that I'm summing up, these weights change. Right? What's the sum of these weights? 1. That's right. That's the whole reason we're average. We're weighting them, and the sum is equal to 1. What would a weighted average be? Right. You could call this as alpha 1 x1, this alpha 2 x2, or we have these alphas are between 0 and 1, and they sum to 1. Right, sometimes places where a weighted average might make sense, just arithmetically. Right, we can write, let's write the call this x. The unweighted average of 3 terms, we know is equal to 1/3 x1 plus 1/3 x2 plus 1/3 x3. What if we don't observe x1 and x2, but we observe their average? Well, I know that I'm not going to weight those two the same way, right? Because it's already an average. Right? So I can already do the math here from the sum to 1. This will be equal to 1/3. And this will be equal to 2/3. So I would use a weighted average, right, to average one more observation with the previous average to get, as a result, the unweighted average, right? So this weighted average can be, it also seems a very natural concept, and it's kind of, it's a measure of the importance, right? In some sense, of these two terms, this first term is the most important for our average because it contains two other terms. It's already like it's not just one, it's already got a whole bunch of them in there. Okay? So we're going to weight it more highly because it's more important for our average. That's what we want to do here with our pricing equation. That's what we see with our pricing equation. We have our weights. We have the weights 1 minus beta theta. I'm just going to call everything in there t plus 1 minus beta theta x plus 1 t. No. I forgot the most important term. The weight. Theta xt plus 1 t plus 1 minus beta theta squared xt plus 2 t dot. So we have, if we sum up all the weights, we get 1 plus beta theta plus beta theta squared. It's a geometric average. We did this together last week. All right. This is simply equal to 1 over 1 minus beta theta. That's why that term's up front there. So these sum to 1. Right? These are all betas between 0 and 1, thetas between 0 and 1, the product is between 0 and 1. Right, so we have exactly, right, the conditions fulfilled for it to be weights for an average. Okay? So it's exactly a weighted average of all current and future marginal costs. We're weighting them, we're taking an average of them, but it's not a straight up arithmetic average, it's a weighted average. Some of these terms are going to be more important. Which terms are more important? Well, those with the higher weight, and the higher weight, this beta theta is a number between 0 and 1, so if you take it to a higher power, it gets smaller and smaller. That's why this series converges. So the closer we get to today, the higher is the weight. Well that makes a lot of sense. You know, that when we're making our pricing decision, things that happen on the future are important, but the sooner something happens, the more important it's going to be. Why? Well, our owners are impatient. They don't care a whole lot about the future to begin with, and on top of that, the price that we choose today might not be around far in the future anyway, right? Or it's less likely to be around. Right? So something that's going to happen in 10 years is less likely to affect or to be relevant for a pricing decision today. And even if it is, our household doesn't care about that much anyway. Right, another way to write this, if we write this instead of the log deviation of marginal cost from this steady state value in terms of just the actual log of the markup, then we get here what I was saying here. This optimal price is the weighted sum of these current and future nominal marginal costs, right? And that here is the frictionless gross markup in logs. This gives us the optimal price in our steady state. All right, so optimal price in steady state is going to be equal to the frictionless markup, right, plus a weighted average of current and future marginal costs. Right, if we had equation 27 with, let's go back to the frictionless price level. This would give us PG star is equal to mu plus 1 minus 0 times, well, if theta is equal to 0, then everything except the first term disappears. So we're just going to get then a marginal so we compare it up there, we have our, so it's the log from PTI equals markup times real marginal cost times the price level. So we get the nominal marginal cost. And now if we take logs, exactly what we have. That's just our pricing equation in logs, so we get this nice additive multiplicative, and also then for the complicated case when theta is not equal to 0, we have this linearization, which is going to allow us, which allows us to write it in this convenient form here. Hallo Volker. Ja, alles gut. Tschüss. Oh no, that's the microphone on. Yeah, so our interpretation, our optimal price is the markup over this weighted average of current and future nominal marginal cost. So this tells us exactly where the starting line should be. Right, we know it's going to be in between these two. It's going to be in between the price today and the price of tomorrow, but it's going to show us, right, you saw here, as this probability being stuck with this price goes down, we're going to move closer towards what the optimal flexible price would be today. Right? But this gives us exactly by how much, how strong we weight these. And we weight these two in a very intuitive way. One with this probability, and two with our owners, the household's impatience. Okay. So now how can we bring our firms together with households now? All right, so goods market clearing has to hold in every market, as we have here. There's only consumption. We don't have I or G or NX. But we're only going to sell as many goods as are demanded for each good I, and we're only going to, the price is going to adjust, or our production will adjust to meet that demand. We're going to set the price and adjust our production so that YTI is exactly equal to what's demanded at the price that we set. All right, if we aggregate up, we're going to get our aggregate consumption out of that same perspective there. Right, the total amount of the basket sold produced is the total amount that is consumed. All right, then we can take our household's consumption Euler equation and turn this into an equation that relates. Ooh, look at this carefully. We have Y and I being related negatively. Remember last week when we were looking at a goods market equilibrium on the first day, when we got to the IS equation, and it was a downward sloping curve in Y I space. So that's this. Specified and from first principles, from household optimization with market clearing. And we see a couple of interesting points here where it differs. We have explicitly the connection to the real interest rate here. Right? So if we look in terms of non-interest rate, we have expected inflation, and we have household expectation of future consumption, here then of future production. Okay. Our labor market, it's a little trickier. Right? Our clearing of the labor market requires us to sum up over all the labor demand of the firm. So in other words, we have a representative household. So our household provides NT and works in all of our individual firms. Right? Or you can think about it, you have a big family. Our optimization problem for the household, it's the union of a big family. I don't know. I come from a Catholic family. My mom has a total of 6 brothers and sisters. I have 27 cousins. Right? I've got in my family. I have a doctor. We have a professor. We have someone who works in a computer store. Someone who teaches gymnastics. In our family, we have someone working in every firm I. Yeah? So think of it like that. Yeah? So we have our household's labor supply, our family's labor supply, and there's someone in our family working at every firm. Yeah? Okay, let's see if we can, what's the goal here? The goal here is to find something like an aggregate production function. When I look at equation 14, if I can just erase the i's, then I would have, right? I've seen every macro course an aggregate production function, right? Except we've got the capital subsumed into A. So maybe we can solve that firm production function for NTI. We substitute that in here. And, with this AT, we get to pull out front. What happens when we integrate over all the YTI's? Right, the YTI's are related to YT, not directly, but we have, remember our demand function. We have these different prices. And so we get an aggregate production function. If we were to ignore this part here, we'd have exactly an aggregate one-to-one version of the firm production function. So we have this last term here. This last term here, what does it depend on? Well, let's make it disappear. Let's have all firms choose the same price. And this price then is then equal to the price level. So if PTI is equal to PT for all I, then this is equal to 1, and this whole term is equal to 1. So we have the aggregate production function is completely analogous to the firm level one. If these prices aren't all equal, right, if we have some variation in our prices, remember, they shouldn't vary in the sense that all firms face the same or symmetric demand functions and have the same or symmetric production functions. There's no fundamental underlying reason for these firms to have different production functions, to produce a different amount. But they will if their price is different. And so in the aggregate, we're going to find that we have lower output than we otherwise would because of price dispersion, because prices are going to be dispersed around the average. And we can write this then out, take the logs, we get equation 33, and we have this dispersion term. Now the nice thing, in our first order approximation, this dispersion term disappears. Remember, by construction, right, our price level, the aggregate price level, is the average. Think of it as like the average price. So the first moment, the average, right, on average, PTI is equal to PT. So any effect of DT must be coming from either the distribution, how widely dispersed they are, or whether this distribution is asymmetric, if there's skewness to one side or the other, or if there's a fourth moment of excess kurtosis, or this. These are all higher order components. The first order component is, think of just averages. The average of PTI is PT, so up to a first order, it disappears in D. And so we have, at a first order approximation, exactly a linear, log linear production function, Cobb-Douglas, that you've seen since your master's studies. Okay, then we have our real marginal costs. Right, where do they come from? This is always, so our firm real marginal cost. Firm's production function YTI equals AT LT I 1 minus alpha. All right, so to produce, right, AT is a technology that's given exogenously. Right, so the margin, the input that our firm gets to choose is LTI, right, the labor input. So what's the cost of our labor input? The wage. Right? WT is the cost of labor. Right? So if we're going to write out our profit function, right, we would write then, so firm I is going to be equal to WT LTL. That's the costs. And so the marginal cost of this is not the wage. Right? This is surprising. You have to stop and think about this for a second. The marginal cost of labor is the wage. If we increase our input by 1 unit, we have to pay the wage. Right? 1 more hour of labor costs whatever the wage is. We have to be a little more careful. When we talk about marginal product or marginal cost, we're talking about the marginal cost of a unit of production. Not how much does 1 more hour of labor cost us, that would be W, but how much does 1 more unit of our good cost? How much does 1 more unit of what our labor is producing cost? So we can if so let's choose a number that's round. Let's say that the wage is equal to 10,000 dong. 10,000 dong for an hour of labor. Is that number really high or really low, or would you say that's like somewhere in the realm of possibilities in Vietnam? I'm not even sure what would an hourly wage for an average hourly wage be like in manufacturing at a shop that makes textiles. So 20. You say 20. You say less than 20 or
No, over 20.
more than 20? More than 20. Okay. All right. Then let's do 30,000 dong. That sounds like a reasonable wage then, right? Okay. So 30,000 dong is called what an hour of labor costs. If this takes 30 minutes to make, and this takes 2 hours to make, the marginal cost, so the cost of producing 1 more of these, is 60,000 dong. The cost of producing 1 more of these is 15,000 dong. So we have to take the wage, which gives us the cost of 1 more unit of labor, and we have to transform that unit of labor into units of production of the good. So let's find our, right? This is the nominal. That's a real. So the nominal marginal cost of production is cost of or unit cost of labor. Right, that was 30,000 dong in the example. And then we need one unit of labor could produce 2 of these in an hour. So we divided the 30,000 through by 2 to get this. 1 unit of labor, 30,000 dong, but we need, or 1 hour of labor can produce half of a marker. We needed 2 hours to produce one of these. So 2 hours to produce one of these markers. So we took the 30,000 dong wage and divided it through by 1/2. The marginal product is labor. 1 hour can produce 2 of these, or 1/2 of these. And of course, to get the real marginal cost, then we divide through by the price level. So we take the real wage divided through by the marginal product of labor. All right, marginal product of labor is to take our production function and take a derivative. Take the derivative with respect to labor. How much does our production change if we added 1 more unit of labor? Our marginal product of labor is positive but decreasing. Remember, each additional worker brings us additional production, but less additional production than the worker who came before. They start to bump into each other more often, or occupy machines or whatnot. If we take logs and substitute the labor demand schedule in, right, our marginal cost is going to be equal to the real wage. We have constants, we have our technology and production. Now, the reason why this is so useful is that if we look at a specific firm, and period t plus k, that last we said its price of t, many of these objects are either constants, are exogenous, or are equilibrium objects that our firm can't affect. The nominal wage and the price level are aggregate variables, right, outside the control of our firms. So the marginal cost in period t plus k of a firm that last changed its price in period t is equal to the marginal cost on average in period t plus k plus a factor, right, of the differing amount of production. Right? And we see here that if you produce more on average, your marginal costs are going to be higher on average. Right? Why? Remember, if each additional worker brings you less additional production than the worker that came before, if you're producing a lot already, you have a lot of workers who aren't very productive because they're getting in each other's way, and to produce 1 more extra unit of the good, you're going to need to hire maybe 2 more of these less productive people, right? Whereas someone who's not producing a whole lot, doesn't have congestion or people bumping into each other, can produce 1 more unit of the good with simply 1 additional worker. Right? This is, think of another great picture in economics for our marginal production. As L increases, we're producing more, but our marginal product of labor is going down. And then you can see, if we wanted to increase our production by, say, 1 unit here, right? We need to increase our labor by that amount. If we increase the same increase up here, we have a much larger increase in labor that's necessary. So the marginal costs of a firm that's producing a lot are going to, or they're producing more than the average firm, is going to have higher marginal costs than the average firm. Okay. All right, so now one more second before I continue here. We're going to stop in just a minute for a break, don't worry. Let's do this side and then do this. So, okay, then we can take this marginal cost relationship and we can get rid of the dependence on the different amount of production, right? Because the different amount of production is not going to be driven by different technologies or different elasticity of substitution. Remember that firms are all symmetric. So any difference in production has to come from a difference in prices. We can bring them back now into this marginal cost, and we get the marginal cost expression here in 39. It depends entirely in period t plus k on aggregate conditions in period t plus k than the last time this price was changed. So why are we doing this algebraic acrobatics here? We went from having to track a measurable infinity of different firms. Firms in the spectrum, firms between 0 and 1, right, in the unit interval. Right? And the idea was, I told you this is going to simplify things. We saw how to simplify the price level into these two components, last period's price level and its optimal price. But now our optimal price, right, we have to keep track of marginal costs in every period of time based on how many, we have a whole set of vintages of marginal cost and price. So our price, right, now we have to keep track of marginal cost in t plus k for the last year's price of t, from the last year's price in t plus 1 and t plus 2. So we've gone from a measurable infinity to kind of like a countable infinity. We have to keep track of all these different marginal cost vintages. The marginal cost of a firm today, the last changed its price 3 years ago, is different than the marginal cost today of a firm that last changed its price 4 years ago. Right? We're going to keep track of an infinite number of objects. Mathematically, countable infinity is a left 0. That's one small measure type of infinity. The measurable, the 0 to 1 interval, it's a larger infinity. Right? So we've gone to a smaller infinity. It's still too much. Okay? What we want to do is now get rid of this vintages. The marginal cost in period t plus k, and we're going to last change its price in period t. And the way we're doing that is we're tying these marginal costs to equilibrium aggregate objects, and then we finally tie it back to this last price adjustment. Okay? So now the only thing that we need to watch on the individual firm level is this. Right? So now we don't have to deal with measurable infinity or countable infinity, but just the optimal price in period t. And reducing all those infinities is a lot for my brain. Let's take a 10-minute break. Okay?